You know that feeling when you're staring at a puzzle and you just hit a brick wall? Well, what if I told you there are hidden doors, secret passages to find those really elegant solutions? Today, we're going to build a mental toolkit that'll help you spot the simple answers hiding in plain sight. All right, let's dive right in.
Okay, let's jump right in with a challenge. Take a look at this rectangle on your screen. You see that kind of unusual shaded area? The question is, what fraction of the whole rectangle is shaded? Now, I know what you're thinking. This looks like a real geometry headache. Feel free to pause and give it a crack. But hey, don't worry if you're stumped, because the solution is surprisingly elegant. It's the perfect example of the kind of thinking we're going to get into today.
So, where do these kinds of puzzles even come from? I'll tell you one thing, you're not going to find them in a typical math textbook. Nope, this one's from a math Olympiad-style competition. These things are designed to test not just how well you can crunch numbers, but how creative you are, how you approach a problem. They're basically a playground for your brain, and they're perfect for developing the mental muscles we're going to talk about.
The puzzles we're actually looking at today, they come from this awesome sourcebook for the Association of Mathematics Teachers of India. And it's just this fantastic collection of problems, all designed to really push students to think way outside the box.
And that really gets to the core idea of what we're talking about today. You don't need to be a math genius to solve these. Not at all. What you need is cleverness. And by cleverness, I just mean, the ability to find the hidden patterns, to spot the shortcuts, and to see things from a totally fresh angle that can turn a super hard problem into something, well, simple.
All right, let's put that idea into practice. Time for our first real puzzle. This one is all about spotting patterns, which is, a crucial skill for any problem solver.
So take a look at this sequence of numbers. At first, it might just look like a jumble, totally random, but I promise you, there's a hidden logic to it. What's the link between 11, then 88, then 16, and so on? Go ahead, I really encourage you to pause here and see if you can figure it out for yourself.
Okay, ready for the answer? The secret is, there are actually two patterns woven together here. It's not one sequence, it's two. So, look at the numbers in the odd spots. The first, the third, the fifth. It's just 11, 16, 21. You're just adding 5 each time. Simple. Now look at the even spots. 88, 80, 72, we're just subtracting 8. It's a really cool bit of misdirection, and it just goes to show how something that looks complicated can be super simple underneath.
So, if we just keep those two patterns going, the next numbers are pretty easy to find, right? We get 26, then 64, then 31, and 56. It's a simple solution, but the trick was looking past the surface. And that's exactly the kind of thinking we're focused on here.
Awesome. So, spotting patterns, that's one tool in our toolkit. But what happens when a pattern isn't obvious? Well, for our next problem, we have to do something a little different. It's not about spotting a pattern, it's about completely reframing the question itself.
All right, let's check out our next puzzle. So imagine a rectangular playground. We've got two runners, Samrid and Saket. Samrid takes the easy route, just running along the outside edge of the perimeter. Saket, though, takes this more complicated zigzagging path right through the middle. You can see exactly what their paths look like.
Okay, so Samrud's path is a plain old rectangle. Saket's path is this whole series of zigzags. Now, your first thought, your intuition, is probably that Saket's path has to be longer. I mean, look at it. But is it?
So that's the question we need to answer. Just based on what you see, who's traveling a longer distance? Samrud on the perimeter or Saket on the inside?
And here is the absolutely mind-blowing answer. Their paths are exactly the same length. I know. So how can that be? It's all about changing your perspective. Think about it this way. If you took all the horizontal bits of Saket's path and just pushed them all up to the top, they would perfectly equal the width of the rectangle. And if you took all the vertical bits and pushed them to the side, they would equal the height. So Saket's crazy path is literally just the perimeter of the rectangle, all broken up and rearranged. It's just a fantastic example of how a simple change in how you look at a problem can totally unlock the answer.
Okay, so far, we've seen how spotting patterns and reframing a problem can be total game changers. For our final challenge, we're going to look at a problem that seems, honestly, almost impossible at first glance. But as you're about to see, there's a hidden rule that can solve it, just like that.
Okay, take a look at this complex shape. How on earth would you find its area? I mean, the traditional way would be to slice it up into a bunch of tiny triangles and rectangles, find the area of each one, and then add them all up, which sounds, well, it sounds like a lot of work and really easy to make a mistake. But what if there was a much, much better way?
Well, you're in luck, because we are not going to be splitting it into triangles. Nope, there's a beautiful secret shortcut, an underlying rule that makes this problem incredibly simple.
It's called Pick's theorem, and it is a truly remarkable little formula for finding the area of any polygon whose corners sit on a grid, and it's so simple. All you need are two numbers, I for the number of grid points on the interior of the shape, and B for the number of points on the boundary of the shape. That's it.
Okay, so let's apply it to our big, complicated polygon. First, we just need to count the points on the inside. If we go through and count them all up, we find there are 14. So I is 14. Easy. Next, we count the points that are right on the boundary line itself. And if you count those, there are 18 of them. So B is 18. That is literally all the information we need.
Now for the magic part. We just plug those numbers into the formula. So we take our interior points, 14, and add half of our boundary points, so half of 18, which is 9. Then we subtract 1. So 14 plus 9 minus 1 equals 22. 22 square units. And just like that, we're done. No complicated geometry, just a simple, elegant rule. It's just a perfect example of how finding that one hidden rule can make a hard problem incredibly easy.
So what's the point of all this? Are these just fun little brain teasers for a math competition? No, not at all. What these puzzles do is help us develop a set of skills for creative thinking that you can use, well, anywhere. Seriously, the strategies we've used today can be applied to pretty much any problem you face. You've got to look for those patterns and shortcuts. You have to be willing to reframe the question and change your perspective. Always be searching for those simple underlying rules. And maybe most importantly, don't ever be afraid to try a totally new approach. These are the real tools of a creative thinking.
So yeah, this isn't just math. It's a toolkit for creative thinking. It's all about building that mental flexibility so you can start to see solutions where other people only see roadblocks. So, I'll leave you with a question to chew on. What problem, maybe in your work or just in your daily life, are you going to look at a little differently now? I hope this has given you some new tools for your own problem-solving toolkit. Thanks for tuning in.